Clickers Academy students, and a massive welcome to everyone tuning in. The wait is over. This is the big one, the chapter that kicks off your entire Class 12 physics journey, electric charges and fields. We are going to nail this entire chapter in one go, covering every single concept, every core theory, and every derivation you need to know. So let's do this. But before we get into the weeds, let's start with a little something I like to call a brain bomber, just to get you thinking. Imagine an electron and a proton are placed in the exact same electric field. Now, which one do you think feels a greater force, and which one is going to accelerate faster? The answer is actually hidden in the physics we're about to break down, so keep that question simmering in the back of your mind. All right, listen up. This isn't just another chapter. This is a mission. With about 45 days left on the clock, our goal is to absolutely conquer electric charges and fields. So let's get focused. Let's own this. Okay, let's dive right in. The entire story of electricity, everything, starts with one main character, the hero of this entire topic, and that is the electric charge. But what even is it, really? The key word you have to remember here is intrinsic. Now, what does that mean? It means it's a built-in, fundamental part of matter itself. Just like you can't take the sweetness out of sugar, you can't take charge away from a particle. It's just there. And this one property is the reason we have electricity, magnetism, the whole shebang. And its SI unit is the coulomb, which, by the way, is also called an ampere second. So don't get tripped up if you see that. Now, charge plays by three simple, unbreakable rules. First up, additivity. Charges are scalars, you just add them up like regular numbers. Symbol. Second, conservation. You can't just create charge out of thin air, and you can't destroy it. You can only move it around. And third, and this is the big one for solving problems, is quantization. You have to lock this one in your brain.
Quantization का मतलब simple है. Charge comes in packets. The smallest possible packet is the charge of a single electron, E. So you can transfer 1 electron, 2 electrons, 100. But you absolutely cannot transfer half an electron. आधे पौने में deal नहीं होती. Physics है, सब्जी मंडी नहीं. And that's exactly why the formula is Q equals N times E, where N has to be an integer, a whole number.
So, we have these charges. Great. But how do they, talk to each other? How do they interact? Well, the rule book for their interaction is Coulomb's law. It tells us the exact force they put on each other. The law itself is pretty straightforward. Basically, the bigger the charges, the stronger the force. And as they get farther apart, the force gets much, much weaker. It's this simple relationship that governs everything from how atoms hold together to a bolt of lightning. And here is the formula that defines that rule. F equals K times Q1 times Q2, all divided by R squared. Now that R squared in the denominator, that is the most important part of this whole thing. It's the famous inverse square law, and it means distance has a massive, massive impact on the force. This makes that inverse square law crystal clear. You bring charges closer, and bam, the force just skyrockets. You move them apart, and it drops off dramatically. और हाँ, अगर charge same हो, तो repel करेंगे, क्योंकि physics भी थोड़ा attitude रखती है. Now here's where it gets really cool. A charge doesn't actually have to touch another charge to exert a force. Instead, it creates this invisible zone of influence all around itself. And this region, this space where its force can be felt, is what we call the electric field. We measure this field's strength by seeing how much force it applies to a tiny little test charge. So the electric field, E, is simply the force, F, per unit charge Q0. For a single source charge, this simplifies to E equals KQ over R squared. And right here is the answer to our brain bomber. Remember F equals QE? Since an electron and a proton have the exact same magnitude of charge, they experience the exact same force. But what about acceleration? Well, F equals ma, right? So acceleration is just force divided by mass. And since the electron is much, much lighter, it experiences a far, far greater acceleration. See? It all connects. To visualize these invisible fields, we draw what we call electric field lines, and they follow some very strict rules. They always start at a positive charge and end at a negative one. They can never intersect. The tangent to any point on a line shows you the field's direction right there. Where the lines are closer together, the field is stronger. And finally, the electric field inside a conductor is always, always zero. So, Why is that never intersect rule so strict? Well, think about it. The tangent to a field line shows the direction of the force. So if two lines crossed, you'd have two different tangents at that single point. That would mean the force is pointing in two different directions at once. A charge placed there literally wouldn't know which way to go. It's physically impossible. So what happens when you take a positive charge and a negative charge of the exact same strength and place them really close together? You create a fundamental structure that you see all over physics and chemistry, the electric dipole. Think of it as the power couple of electric charges. And we describe this power couple with a single vector called the electric dipole moment, or P. Its magnitude is simply the charge Q multiplied by the separation distance, which we often call 2a. And its direction, and this is super important, is always from the negative charge to the positive charge. So this dipole creates its own electric field. Along its axis, what we call the axial line, the fields from the two charges don't completely cancel out. For a short dipole, this results in a field that weakens much faster than a single charge. The final formula is E equals 2kp divided by the distance cubed. And notice that it's distance cubed, not squared. That's because the fields from the two charges are kind of fighting each other. Now what about the line that cuts perpendicularly right through the dipole's center, the equatorial line? Here, the vector components of the fields also interact, and we get a different result. The formula is kp divided by the distance cubed. The form looks similar, but the strength is definitely different. And this right here is the most important takeaway. For the same distance from a short dipole, the field on the axial line is exactly twice as strong as the field on the equatorial line. This 2-to-1 ratio is a classic exam question, so make sure you remember it. So, what happens if we take our little dipole and we place it in an external electric field? It doesn't just move, it experiences a turning force. It wants to spin, and this rotational effect is called torque. Here's how it works. The external field pushes the positive charge one way, and it pushes the negative charge the opposite way. These two equal and opposite forces create a couple, which generates a turning effect. This torque will try to rotate the dipole until it aligns perfectly with the field lines. And the formula for this torque is tau equals Pe sine theta, where P is the dipole moment, E is the field strength, and theta is the angle between them. Now that sine theta is the key. It tells us the torque is at its absolute maximum when the dipole is perpendicular to the field, since sine of 90 degrees is 1, and it's 0 when the dipole is perfectly aligned with the field, because sine of 0 degrees is 0. And there you have it. From the fundamental idea of charge, to fields, to the dipole and its spin, you've just seen how all these concepts logically build on each other. This chapter isn't about memorizing formulas. It's about understanding these core building blocks. Once you grasp the logic, the marks will just follow. You put in the work and you understand the concepts. Now go out there and own it. Feel the field, live the charge.